and I welcome you to the second day of week 2 of this course. In the last class, we learnt about finding out symmetry operations that can be generated from any given symmetry element, and we also learned how to combine these symmetry operations. So, in the last class, we left at a place where we were thinking about possibility whether an assembly of or the collection of all these symmetry operations for a given molecular structure can form a group. We will see that today. So, what are the things that we need to form a group? We need to have a set of elements and a binary operation defined in it. So, and then we should follow certain rules, that is all the elements of that particular set. If we take any two of them, the product of those two, that is the combination of those two elements, will produce an element which should be a part of the set. So, similarly, a square of any given element also should be within the set. It is called closure property. Similarly, there should be an identity element for each and every set to be which is a necessary condition for forming a group. There should be an unique inverse for each and every element of the set, and lastly, it should follow the law of associativity of multiplication. Now, let us see if our symmetry operations can do the same thing. So, what are the ways to find out whether collection of symmetry operations will form a group or not? Let us have a look at that. So, what are the things that we need to do in order to find out whether some symmetry operations belonging to a particular molecular structure will form a group or not? First, we have to determine the shape of the molecule. Okay. So, once I know the shape of the molecule, what I have to do, I have to find out all the symmetry elements that are present for that molecular structure. So, if I just take the example of water, so we will be using this example of water and ammonia quite a lot. So, for this water molecule, we have seen that what are the symmetry elements that we have? We have an C2 axis here. We have a sigma plane which contains all these atoms. So, we have sigma V, and we also have another sigma plane which bisects this HOH angle, and we call it as sigma V prime. And obviously, identity must be there for any given structure. So, we have identity also. So, if you try finding out, you will see that there is no other symmetry operations can be possible, because all these are symmetry elements to start with. We located the symmetry elements, and the symmetry operations generated by these symmetry elements are nothing but sigma V itself, sigma V prime, identity, and C2, because if you operate C2 twice, it will give you identity. So, the total number of symmetry operations, possible symmetry operations are identity, C2. If you call this axis as Z axis, you can specify even this C2 as C2Z. You can call it X, Y, whatever, and you can write like C2X, whatever. Okay. So, mostly the molecular axis is taken as Z axis. Okay. So, other than that, you have sigma V. This one also you can specify, like if I take this axis as Z axis, so I call it C2Z, and the plane which contains the molecule, if that is the XZ plane, then that means if this axis is the X axis, then that will be called sigma XZ, and the sigma V prime, that will be actually the YZ plane. So, you can even specify, that will help you actually. Okay. Now, these are the possible symmetry operations. With this list of symmetry operation that is possible for this molecular structure, we will try to find out whether it will form a group or not. So, the first thing is whether the closure property is verified or not. If you just think about what we learned last class, we take this same example and we showed that a combination of sigma v and sigma v prime gives you the exact same result, that is produced by C2Z alone. So, essentially what you have is sigma v prime on a given structure will give you exactly the same thing as operated on the same structure. So, I can write that sigma v prime is equivalent to C2Z. Okay? So, what we learned from here is that the combination of any two symmetry operations will produce another symmetry operations which is already present in this particular set. If I call this one a closed set, then C2Z is already present there. We can try anything, like if we operate C2Z and sigma v one after another. So, what you will see, C2 will just rotate this structure here, and sigma v, which is we have written like sigma v xz. Okay, sigma v xz is just the molecular parent, so it will not do anything. So, this is as good as the effect of the other sigma plane, that is sigma v yz or sigma v prime. So, the effect of this combination will produce the sigma v prime, which is already a member. So, if we keep on trying different combinations, we will see it will produce some symmetry operations which are already a member of this set. That means this set is closed. So, closure property is satisfied. Very good. Now, next thing is we will try to look for identity element. We do not have to ask anything, it is already there. E operating on anything produces the same thing, it is do nothing. So, identity is present. So, I have one closure property satisfied, I have an identity already. Now, let us look for the presence of unique inverse. Okay, forget about E because E is its own inverse always. What about C2Z? Now, we know that C2, if I operate twice, it gives you E. So, you have C2Z followed by another C2Z, is nothing but identity. That means C2 is its own inverse. Okay? So, for C2, we already have its own inverse. Similarly, sigma v by its own character, they are inverse of themselves. So, sigma v is its own inverse, sigma v prime is its own inverse. So, there is a unique inverse for each and every element of this set which are constituted by these symmetry operations. Okay? And lastly, if we look for the associativity. So, what does that mean? So, say if I have sigma v and sigma v prime, and if you operate C2 on that, will it be same as C2 operated on sigma v and then sigma v prime? So, if you check this one, I will leave it to you. You try this one out and find out if these two are same. However, I will tell you the answer, yes, that will be exactly same. So, it does not matter how I am doing these operations, that is going to give me the same result anyway. So, the law of associativity also holds. That means this set of symmetry operations for water molecule forms a group. Okay. So, this one is now called a group, and I can tell you you take any given molecule, any structure, once you have found out all the possible symmetry operations and you check for this conditions to form a group, you will find that every molecule will form a group when someone uses all the symmetry operations that is possible for that molecular structure. So this is verified now. You can try out with different molecules like ammonia, which is another simple molecule. So you know what are the symmetry operations there. Okay, so you find out symmetry elements. So you find out the symmetry elements first, and from there you find out the symmetry operations. Okay. Now if you can generate all the operations, then you have found the total list of the symmetry operations. You can verify whether you have found the exhaustive list of symmetry operations for a given molecular structure. You can also do the binary combinations of any two symmetry operations that you have already generated. Okay, and ultimately you will see that you cannot generate any other symmetry operations. Okay, that means the set is closed. Okay, so now we figured out that this symmetry operations form a symmetry group. We call it symmetry group. Okay, because we want to just differentiate this particular type of group from any other mathematical group, because we are utilizing something special as the elements of the group, that is the symmetry operations. It's also called symmetry point group, or it's also called simply point group. Okay, so why this is called a point group or symmetry point group? Because in in a given molecule, when I operate all the symmetry operations on the structure, what I do is I at least keep one point in that molecular structure unchanged. The others may change their position going for another indistinguishable structure, but they may change their position. But there will be at least one point which will remain invariant to any of the symmetry, all the symmetry operations. So that is why this group formed by the symmetry operations are known as symmetry point groups or simply point groups. So we saw that these symmetry operations can form the symmetry point groups or point groups. Now, how do you find out what type of group? So we need some kind of a procedure, and also we need some nomenclatures for this point groups, because say you can see like the symmetry operations for water molecule is not the same as that of ammonia, which is not same as that of benzene molecule. So for different molecular structures, there are different sets of symmetry operations, thereby they will form different types of group. Their properties will be different. So there are ways to differentiate different groups, and we are going to discuss about that right now. So you will before I go to this, I will tell you like maybe I will look at this particular page here on your screen. So you can see that there is something called point group here on the top of the table, and then if you look at the column, you will see something like C1, C2, C2V, D2H, C infinity V. There are so many symbols. So these are the names of the point groups. Okay, we will know how to find that out. Okay, and it is possible, as you can already understand, that several different molecules can have the exact same list of symmetry operations. So thereby they will belong to one same group, same point group. Okay, that is the beauty of this whole group theory and applying group theory to molecular symmetry problem. Let's come back to our discussion of how to find out which point group one particular molecular structure belongs to. So, as I was saying, first you determine the shape of the molecule. You can use the Lewis structure and apply the VSEPR theory, which I am not going to discuss because I assume that most of you, all of you know this VSEPR theory. So, find out the structure from using this theory, and it is highly recommended that you use a model to determine what are the symmetry operations that are present. So, at least you find out the symmetry elements, and from there you find out what are the symmetry operations like, and then what you have to do, you have to use a kind of systematic procedure to find out which point group your molecule belongs to. So, what is that procedure? So, few things you have to do there. First is you have to, if you look at on your screen, these points are written there. So, first you have to find out what is the highest axis of rotation. Okay. So, what is the Cn? And next you have to find out if there are other axes of symmetry, okay, other than that principal axis of symmetry Cn, do you have any other axes of symmetry which are not coincident? And then you have to also look for the mirror planes. Are there mirror planes? So, these three mostly if you look at, you will be able to go to the next step, that is following a systematic procedure and finding out what point group your molecule belongs to. So on your screen you have a flow chart which actually summarizes that so called systematic procedure, how to find out to which point group your molecule belongs to. So, after you found out your molecular structure and figured out what are the all symmetry operations that is present for that molecular structure, you start here. What you do in the first step, step 1, it says you have to first ask whether this structure belongs to a spatial group. What do we mean by that? We will come to that in a very short moment. So, in this spatial groups we have linear groups. Okay. So, what does linear molecules. So, what do you mean by a linear molecule? Linear molecule will be something like this. So, if this is a molecule, say for example carbon dioxide, that will be a linear molecule, okay, and that will belong to a spatial category of group. Okay, so you can easily figure out by looking at the molecular structure whether your molecule is linear or not, and based on that you can categorize them by giving them some spatial groups. We will come to that. And second thing you can ask is whether our molecular structure that is under consideration has multiple higher order axes. What does that mean? When I say higher order axis is if any Cn where n is greater than 2. Okay. So, if suppose for example C3, I have a C3, I will look for any other C3 in that particular molecule or not. I am talking about the elements. Okay. So, there are possible certain molecules, say for example if you take methane. So, a methane has 4 CH bonds, and along each CH bond you have one C3. So, ultimately you have 4 C3s for CH4 molecules, and CH4 has a tetrahedral structure, and also the point group is a tetrahedral point group, or is known as TD. Many of you have come across this term TD, but probably you did not realize what that TD means. Now you understand what that TD means. And similarly, you can have structure with octahedral symmetries or icosahedral symmetries. So, all these things will give you some spatial group like T, O, OH. OH also you are very familiar. All right. So, that was the step 1. So, step 1 will give you certain spatial groups. Now, once your answer to that question, that whether the molecule is linear, and second is whether the molecular structure has multiple higher order axes, then you go to step 2, and in step 2 you ask whether there are any proper axes of symmetry, if the or even improper axis of rotation, and if the answer is no, then you have certain type of groups which are like C1, Cs and Ci. So what are they? So if you do not have any other operations other than identity, your point group is C1. If other than identity you have only a sigma plane, one sigma plane, then you have a Cs point group. Then if you find a molecular structure where inverse is the only operation other than identity which is present in your molecular structure, then the point group of that molecule will be Ci. Okay? So this will be some special cases. Now if the answer is that no, I don't have I may not have a proper axis of symmetry, but I have an improper axis of symmetry, then you go to step 3. Then the question is the question that you ask is, do I have only improper axis of symmetry Sn with n even? If the answer is yes, that is I have only say S4, S6, S8, then and no other elements other than identity and this, then what you have is an group which is Sn. This is for n equals to even. Now if answers to all these questions are no, then what you go to step 4 and step 5 here. Okay. For those structures which do not belong to all these step 1, step 2, step 3 type of groups, then you ask that whether the molecule has a Cn axis, that is, does it have a proper axis of symmetry? Because in the previous cases, what we saw, either is a linear type of molecule which has like infinite number of rotational axes, or you have a many Cn axes, or you have structures which has no other symmetries other than S, that is sigma, or I, or even nothing other than identity, or you had a case when you had only Sn other than E and n is even. Now Sn, when n is even, you always have an Cn by 2. We discussed that in the previous class. So when I go to the next step, when I ask, okay, do I have only one principal axis of symmetry, Cn, and that time I should ask, is that Cn a consequence of an even order Sn? If the answer is no, then I proceed further. That means I have one proper axis of symmetry, and that proper axis of symmetry is like unique. I do not have multiple proper axis of symmetry, and this Cn is not a consequence of an even order of improper axis of symmetry. So after finding this one, I ask that, okay, do you have certain C2 axis perpendicular to this principal axis of symmetry? So I look at this step. So the answer may be yes or no. So if yes, then you go to step 5. If no, you go to step 4. Okay. So step 4 take you to the point groups which has a Cn axis, single Cn axis, and but there are no perpendicular C2 axis to this principal axis of symmetry, and this particular type of molecules, they belong to C type of point. Also at a after C, but you start by looking at, so like when you have this step 4, it will give you C type of point group. And when you look at when you find that there are n number of C2s perpendicular to the Cn, you have a type of group which is D type. So D type of group will come from step 5. So when the answer is yes to this possibility of n number of perpendicular C2 to Cn, then you have either C or N type. Now let's follow the direction of this step 4, okay, where I have a C type of point group. Now next I ask, do I have a sigma H? I know what sigma H is because we have discussed that. So if the answer is yes, then I have a point group which is CNH. Okay. If the answer is no, then I ask the next question, which is, well, are there n number of sigma V's? If the answer is yes, I have a point group which is CNV. If the answer is still no, that I do not have sigma H, I do not have sigma V, then the point group will be Cn because it has no sigma plane. So you remember in the previous slide on the screen, I told you that what are the things that you should look at is the principal axis of symmetry, then other axis of rotation which are not coinciding with this principal axis of symmetry, and then you have to look for the sigma planes. So exactly that's what we are doing here. If you look at, so in step 4 we looked at the possibility of other rotational axis which are not coinciding with Cn. Here in this particular case we ask whether they are perpendicular or not, and then we look for the possibility of the sigma planes, different type of sigma plane, and according to the availability of the sigma plane, sigma H, sigma V, you have either CNH or CNV point groups. And if you do not have any sigma plane, but if you have a proper axis of rotation Cn, then you have the point group Cn itself. Now if we go back to the side of step 5, where I found n number of C2s which are perpendicular to the Cn, then I ask my following question. And before that itself, I am I can say that these molecules which has n number of perpendicular C2s with respect to this Cn, they belong to D type. Okay, so that I wrote here. Step 5 will give me D type of point group. So now similar to this C type, we ask the same questions to these guys again. Is there any sigma H? If the answer is yes, D and H is the point group. If the answer is no, next question will be whether there are sigma Ds. If the answer is yes, then I have D and D. And if there is no sigma, then I have a DN point group. Okay. So now you notice one thing here, we call as D and D. You know what D and D is. Okay. So this is the overall procedure to find out the point group of any given molecular structure. Now let's quickly have a look at the little bit detail of this part, that is step 1 and step 2 particularly. Step 3 I have already discussed in detail. So step 1 and rather 1A and 1B, let's have a look at it. Okay. So when I ask whether the molecule is linear or not, if the answer is yes, then the next question I ask is whether the molecule has I, inversion symmetry. If the answer is yes, then I have D infinity H. For some reason this infinity sign is not coming, it looks like a tilde, but this is actually infinity. Both this one as well as this one, they actually are infinity. So if the answer to the possibility of inversion center is yes, then I have D infinity H, and if the answer is no, then I have C infinity V. Now if the molecule is not linear, then I have a next question, whether we have multiple axes of higher order axis of symmetry that I already discussed. So more than 2 if you have more than 2 Cn if you have, where n is also greater than 2. Then if the answer is yes, you ask the next question, that is whether does the molecule have inversion center. If the answer is yes, then you ask certain questions like, does it have a C5? If the answer is yes, then you have an icosahedral point group, that is IH. If the answer is no, then you have octahedral point group or OH point group. And if the answer to this particular question of inversion center, existence of inversion, is no, then you have a tetrahedral point group or TD point group. And once you have cleared through all these questions and your answer is still no, that you don't actually belong to all these point groups, and neither you belong to this SN type of point group, then you move to steps 4 and 3 and so on, as I discussed in the last slide. So we will stop here today, and I will urge you to try out several molecular structure, finding out the symmetry elements and then symmetry operations, the exhaustive list of symmetry operations, and then you use this framework, that flowchart that I showed you, very systematic way of finding out the point group to which your molecule belongs to, and you will definitely learn this whole topic quite easily with a little bit of practice. Thank you very much.